Hello and welcome back. Today we are going over section 3.1 on linear functions and their properties. So for starters, to explore some of these properties, we'll start with the generic function f of x as m times x plus b. Point f of x sub 1 would be m times x sub 1 plus b. So here m and b are in the set of real numbers. F of x sub 2, similarly m times x sub 2 plus b. Recall slope is change in y divided by change in x. So our change in y's, our y values, we had m times x1 plus b. Our other y value, m times x2 plus b. Change in x, x sub 1 minus x sub 2. And you can pick whichever y value you would like to go first, as long as you're consistent, and pick the corresponding x value to go first with it. So our slope then, a little bit of simplifying up top, m times x sub 1 plus b minus m times x sub 2 minus b. So I distributed the negative sign over x sub 1 minus x sub 2. We have a plus b and a minus b. Those will cancel each other out, add to 0. Up top I have a common factor of m, so m times x sub 1 minus x sub 2 over x sub 1 minus x sub 2. So now we've done an actual proof that our slope is m when we have a function written in this form. As far as increasing, decreasing, and constant, when we have just linear functions, all we need is the slope. So if m is greater than 0, f is an increasing function. M is less than 0, f is a decreasing function. And our third option, m equals 0, f is a constant function. So unlike our graphs with curves, we don't have local extrema if we just have a plain linear function. All right, so one common application of linear functions would be the idea of straight line depreciation. So the idea behind what straight line depreciation is, it's really kind of a bit of fiction to make things like taxing and valuing inventory of a business easier to track. Just like our possessions, like cars, depreciate in value as we use them and wear them out. Equipment for businesses does the same. So if you look at, for example, the value of a car, with respect to time, if you buy a brand new car and you drive it off the lot, that's the most expensive drive you take in that vehicle. huge depreciation just from driving it off of the dealership lot. It's now made the transition from a new car to a used car. Even if it's a used car with 20 miles on it, it's a used car now. And it drops and kind of steadies out, and the value changes a little bit less over time. Sort of an extreme example, but say a used car from the mid-90s, making it 1 year older isn't going to change its value all that much as we go on. So it'll eventually kind of flatten out. But the idea is that generally these curves are a little bit harder to keep track of. So what we do is basically do the average yearly depreciation. So basically we look at 1 point when it's brand new, 1 point when its value is considered 0. It's at the end of its useful life. And we say, okay, well, we'll write it up as if it had this trajectory of value instead of trying to keep track of this much tougher model. So we'll just kind of run through an example. So a $120,000 machine is expected to have a useful life of 6 years. So we're going to find the average yearly depreciation for the machine, and then we'll write a function describing the value of the machine with respect to time. So our value will be variable v, time will be, as usual, lowercase t. Typically I try to use sort of a t with a little tail on it just to not get it mixed up with a plus sign when I'm writing these out. So our average yearly depreciation, that would be basically a slope. So all told, we're losing $120,000, and that's happening over a span of 6 years. So on average, machine loses $20,000 in value per year. This is then basically like our slope. So that's our answer to part 1. To part 2, creating a model. Well, we now basically know slope is negative 20,000 over 1. If you like it over 1, we'll just keep it as negative 20,000. So then we use change in instead of y, change in value, equals slope times, instead of change in x, change in t. So the 2 points we have on this, at t equals 0, the value was 120,000. At t equals 6, the value was 0. So we'll just use the second one just because it has smaller numbers. It doesn't matter which one we use. So V minus 0 is negative 20,000 times T minus 6. So V equals negative 20,000 T plus 120,000. And then we can express that as a function, so we will call that our V of T. Value with respect to time, negative 20,000 T plus 120,000. So another common problem is supply and demand functions. Those will sometimes obey linear models. So S of P is typically a supply function. So P is price, unless otherwise noted, will be in dollars. S is the quantity a company is willing to supply. To whatever region or market that they're in. At that given price point. D of P, demand in the region at price B. So how many are consumers willing to buy at that price? So, for example, we might be given D of P is negative 20 times P plus 16,000, and that S of P is worth 60P minus 6,000. We might be asked to find the equilibrium price and equilibrium quantity. So in other words, we're figuring out the price point where the number the manufacturer is willing to provide for the market at that price point is equal to the number the public is willing to buy at the same price point. So basically, if it's selling for too cheap, it's not worth the producer's time to supply it. If it's selling for too much, customers aren't willing to buy it. So we have to sort of find a place in between. So basically, we just set the equations equal to one another. So in this case, negative 20p plus 16,000 is worth 60p minus 6,000. And so we'll just go ahead and solve that equation. Let's see, did I copy these correctly? Yes, okay. All right, so we have negative 80 times p. So I'll just subtract 60p on both sides. And then we will subtract 16,000 on both sides. So negative 80p is negative 22,000, and we'll divide both sides by a negative 80. So then P is equal to negative over negative will flip us back into the positive. So P is 275. So that's the equilibrium price for this item. To find the equilibrium quantity, we plug it into either one. So D of 275, negative 20 by 275 plus 16,000. $10,500. So the equilibrium quantity is 10,500 units of whatever we're selling at $275 each. So don't forget your what types of units these are measuring. One's measuring dollars, one's measuring units sold. So then one more sort of linear application we take a look at here, inequalities in linear functions. If we let f of x be negative 3x plus 7 and g of x be represented by 5x minus 19. That would ask us to find all x st such that f of x is less than or equal to g of x. So this is another one where we're simply using substitution and solving it. So f of x, negative 3x plus 7, we want that to be less than or equal to g of x, which is the 5x minus 19. So subtract 5x on both sides, subtract 7 on both sides, and negative 8x is less than or equal to negative 26. We'll divide both sides by negative 8. And an alarm bell should be clanging in your head. We're dividing both sides of an inequality by a negative. We have to flip the inequality. Remember, that happens anytime you multiply or divide both sides of an inequality by a negative value. So x is greater than or equal to, that'd be 13/4. So then our x is where this happens. 13/4, so 4 will go in there 3 times with 1 left over, so 3 1/4. And we are allowed to use that value, and we are approaching positive infinity. So you can either write it up in interval notation or in set builder notation. Then we'll act such that x is in the set of real numbers, and x is greater than or equal to 3 1/4. Okay, so that should give you enough to sort of practice with in section 3.1. So I'd recommend 1 through 12 all, 13 through 27 odd, and let's see, 33, 35, and 39 to 45 odd. And of course I'll try to make a rough equivalent in the My Math Lab as well for those of you taking that route. Any questions, please feel free to get in touch with me. Otherwise, I'll see you next time.